Hey everyone, I hope you enjoyed your weekend. Let's get it. My name is Mr. Vitier. Very excited to be here. Let's give it a second so this computer could load. Um, my daughter scored a basket the other day and I lost it. She also rejected somebody and she got a nice rebound. So very excited for this week. Let's go. Unit 4. So plate tectonics, soils, atmosphere, wind, El Nino, the tropics of Cancer, and Capricorn. Let's put it all together. Let's start with this beautiful picture of what some of you are probably eating on a daily basis. Hopefully you aren't, but I understand the struggle right now. This is a picture of a hot pocket, right? I like to explain the mysteries of the universe with a hot pocket analogy. Well, let's just imagine when you get home, you put a hot pocket in the microwave, and I think it's 2 minutes and 30 seconds or a minute and 30 seconds. And, you open up the package or you slide it out of its sleeve, and now you're playing with it. You're going like this, and it's hot, but then it starts to cool. And then you start building this confidence, this false sense of confidence, I think, right? And you're like, I can handle it. I can handle it. And then you decide to bite inside of it. When you bite inside of it, the hounds of hell are released and your whole tongue is blistered because now you've just burnt yourself. Okay? That is the tragedy of the hot pocket. Let's try to explain what happened there. Okay? Well, first off, what was the hottest part of that hot pocket when you bit into it? Since you burnt yourself as you bit into it, we would say that the inside of the hot pocket is hotter than the outside of the hot pocket. Now, that's kind of weird, but let's continue to look at that analogy. What cooled first in the hot pocket? Was it the inside or was it the outside? The outside of that hot pocket cooled first because the outside was exposed to air, was exposed to the universe, if you will. The inside was protected by that crusty crust that is sitting on top of it. And so since that crust is sitting on top of it, it is insulating the inside, so the inside is warmer. That makes sense? That is our Earth. Our Earth was a hot magma ball of basically all the elements in the universe or on planet Earth. And as it started to cool, the outside cooled first. However, the inside is still much warmer. All right. So because the inside of the Earth is much warmer, there's a couple of magical things that occur. All right. And so the outside, which is the outside of that hot pocket, forms a solid. So when we look at solid, liquids, and gases, if you cool enough, turn into liquids. Liquids, if you cool enough, turn into solids. Well, we haven't really dug down to the core, all right, the inside of the Earth. So we really don't know if it's a solid, liquid, or gas. Most likely, it's probably going to be a solid. Because of the way waves behave as they try to travel through them. All right. But since it's so hot, it really shouldn't be a solid. In theory, it possibly could be a gas. The other thing we need to take in consideration is the amount of pressure that is pushing on those elements that are in the center of the Earth, which then make it theoretically a solid or a liquid, depending on what book you're really looking at. But just understand that the inside is extremely hot and the outside is cooling, but the inside continually causes these convection cells. Now, if you don't know what a convection cell is, it's basically something that's a reoccurring theme in apes. Hot things rise, cold things sink. And so when we look at the inner and outer core, we're looking at the hot magma is going to rise, it's going to hit the crust, it starts to cool, and then it'll die down again. And on this side, it'll happen as well. The magma rises, and it dives down again. It rises, and it dives down again. This is happening all over the Earth in these convection cells, okay? And this is what causes the movement of tectonic plate activity, all right? So if you ever heard of the theory plate tectonics, this is where that theory comes into existence. Now, what I'm saying is the theory of plate tectonics is basically that the crust of the Earth is moving, okay, and the upper part of the mantle, the asthenosphere, is also moving. So the crust is sliding over the asthenosphere, or I could say the lithosphere is sliding over the asthenosphere. And so there's some vocabulary terms that you would see in your homework, so make sure you're looking at those. All right. So we all need to revisit the different types of plate boundaries, and we need to know the different vocabulary that exists in here. So let's go over these plate boundaries. The first plate boundary is a convergent plate boundary. All right. Now, in a convergent plate boundary, two plates come and they hit each other. Now, very important to know that there's both continental crust and there's also oceanic crust. Two different types of crust. Continental crust is made out of ocean and continents, and oceanic crust is going to basically be the crust that's in the ocean. One is denser than the other. The oceanic crust is denser than continental crust. So what does that mean? If continental crust is hitting oceanic crust is going to go underneath the continental crust. All right. Anyhow, this is going to be an image of two oceanic convergent plate boundaries hitting each other. When that happens, they have a couple of things that can occur. Okay. The couple of things that can occur is one goes underneath the other. All right. Or they could basically come up and try to, basically one is going to go underneath the other. When that happens, there's going to be a trench occurring. So think about it. One is going underneath the other. And now there's going to be a very big hole that's going to be on the bottom. All right. And this upper part kind of folds in on itself and starts forming mountains and volcanoes and areas like that. So let's really look at the convergent plate boundary. A trench is formed, the hole. A subduction plate, that is going down, or a subduction zone. Basically, the subduction zone forms the trench. On this area over here, it's going to fold inside on itself. Volcanoes will start to form. All right, there was a free response not too long ago trying to describe how volcanoes are formed. This is one way volcanic activity or volcanoes are formed. So that subduction plate pushes on that magma, forcing that magma to come up out of the volcanoes. All right, so once again, we get a trench, a subduction zone, volcanic activity or volcanoes forming, all from convergent plate boundaries. We should also think that mountains will form from convergent plate boundaries. All right. So they come together, they converge. The second type of plate is going to be called a divergent plate boundary. This is going to be where new crust is formed. Okay? One plate is spreading from another, another plate is spreading from another, and there's going to be a rift valley, all right? Or basically like an opening, like new magmas coming up, and this is forming. All right, know this one because this is very important because it's the one closest to us. This is the one that's closest to us, meaning in New Jersey, is the Mid-Atlantic Ridge. So ridges are formed from divergent plate boundaries. Also rift valleys. This is just vocabulary to go with divergent plate boundaries. New crust is forming. And we are near the Atlantic Ocean. So if I was asking where is the closest plate boundary towards us, you should know that the Atlantic Ocean is next to us and that the Mid-Atlantic Ridge is right there. All right. Let me go back to the convergent plate boundary. And this is a large trench. And some people think that this is not some people. If you were Googling Marianas Trench, which is next to the Philippines in the Pacific Ocean, that is basically the deepest area in the world. If I wanted to get closest to the magma, we can basically go to mid-Atlantic, Marianas Trench, and that's going to be the deepest place. So I'm mentioning famous things that you should know, like the Mid-Atlantic Ridge. It's in the middle of the Atlantic, and Marianas Trench, which is basically in the Pacific underneath the Philippines. We'll go into an image of that later on. But just understand how this makes sense. And you could just imagine if that's the deepest place on Earth, and it's in the ocean, right? If you were dropping a probe all the way down, or a submarine, I don't think even a submarine can go that deep to the bottom of the Marianas Trench, because it would just crunch up. Think of the temperature change. It would probably get really, really cold, and then it would get really, really hot as you get closer and closer to that magma. It's probably fascinating. There's not going to be any light down there. And I believe they're continuing to do experiments down there currently. All right. Our last type of plate boundary is called a transform plate boundary, and that's when they slide past each other. One's going one way, the other one's going another way. All right. The most famous one that we should know is the San Andreas Fault, which is next to California. If you don't know where California is, that's on the West Coast, baby. Okay. Now, you can have earthquakes on all of these. All right. So you could have earthquakes that get caused all the time. Very often there are earthquakes with transform plate boundaries in California is the ones that we notice. But you could have earthquakes all over. All right. All right, let's continue. All right. So there is this theory called Pangea, which basically was a time when all the continents were together. So this kind of the theory of plate tectonics coincides with Pangea, because if we took all of the continents, they kind of fit into each other. Look at that. South America fits right into Africa. North America fits right into that. If we took Eurasia, India, Antarctica, all these places look basically together. All right. Continents are estimated to move about 1 inch per year. I want to Google that. I'm not necessarily sure, but they are moving. So this supports this theory of those convergent plate boundaries, or these convection cells, rather, continually to move this magma over and over again. Wouldn't it be cool if in the next like 2 bazillion years, North America is going to be all the way on this side of Africa? It'd be crazy. Wouldn't that be crazy, man? That'd be so crazy. All right. Okay. So here is a beautiful image of all of the different plate boundaries. All right. Let's try to know some hot spots that you're going to necessarily need to understand. All right. So if this is the United States, this is that mid-Atlantic ridge that I was talking about. Okay. That's that mid-Atlantic ridge. All right. That's a famous one that you should know. The San Andreas Fault is going to be roughly around here. All right. Now, very important, and the largest plate is the Pacific plate. All right. So if you don't know where the Pacific is, here's the Atlantic Ocean on our east coast. That's our ocean. And the Pacific would be the West Coast Ocean. So that the Pacific plate, look how big it is, all the way around here. All right. The largest plate boundary. All right. And since it's a plate boundary, we call this area over here the Ring of Fire. The Ring of Fire, there's a lot of earthquakes and volcanic activity around this region. Hence, it's called the Ring of Fire. Okay? So we have the Pacific Plate. We got the Nazca Plate. We got this Arabian Plate. And a lot of plate boundaries over here. Plate boundaries are going to give us either some mountains, the Himalayas, all different types of volcanoes and different types of activities. Look at these beautiful islands. So many volcanic activities forming these islands over here next to the plate boundaries. All right. All right, let's continue. Another image of that. Perfect. So I've seen some questions on the early AP exams is trying to ask us, well, what is the composition of the crust, like, element wise? And surprisingly, oxygen is one of the elements that is most abundant in the crust. Oxygen and silicon. All right. Then we're going aluminum, iron, and all those other beautiful things in the crust. All right. Surprisingly, when we are mining something like copper, we're talking about copper's probably not in abundance as much as oxygen and silicon. All right, aluminum there is quite a lot. Iron there is quite a lot. Can't really do anything with oxygen other than breathe. But when we're talking about manufacturing goods, we're not really digging down to the magma. We're basically digging in the crust. All right. So gold and all those other things, notice that you're not seeing those valuable pieces here. All right. So if I were to take this map and look at it on the other map, you would see that mountains are going to form. All right. So that Nazca plate, which was over here. All right. You're going to have the Andes Mountains. And this is, I don't want to overload your head. So put on your helmets. You have the Andes here in South America. All right, that is my my nickname is Andrew. So hopefully you could know that my ancestors came from South America, Ecuador, and maybe that could help you remember that these are the Andes. We live next to the Appalachians, and I'll tell you a story about the Appalachians another time. But some really rough, like salty people, like rough people, like people that really want to do something, like they do something called the Appalachian Trail. And I had my godson. My godson actually attempted to do this, and it's like a hike. Starts in Georgia, and you come all the way up. I believe you end in Vermont, and it's like a nature thing, and you really find out who who you are when you're basically out in the wilds. And so people do this. They camp out and they do something called the Appalachian Trail. You got the Rockies over here. So the Appalachians, the Rockies, and another big one is the Himalayas. All right. And so typically mountains are going to form at convergent plate boundaries. Let's try to take a look at that. All right, or the plate boundaries over here. So we had the Andes, the Himalayas, okay? Not a lot of plate boundary activity in here. Surprisingly, we still do have those mountains that are forming, but we have the plate pushing this way, right? So we have, this is a mid-Atlantic ridge, and this plate is probably pushing this way too, which caused that mountain activity over here. And we have some Rockies over here. All right. All right, let's continue. Here's a really good image where it basically shows you all of the plate boundaries. Let's really concentrate on this image right here. We have oceanic crust pushing on continental crust. The oceanic crust is going to go beneath the continental crust. So it's more dense, so it goes below. As it pushes down, it's pushing this rock on top of each other in mountains. It's going to buckle. Mountains are going to form. Those mountains are forming, and also volcanic activity is also popping out of here. One of the questions previously was like, how do volcanoes form? They typically form at convergent plate boundaries when one plate boundary subducts underneath the other, forming the other land to buckle back on itself, and then that pushes up that magma through there. Here would be an example of a divergent plate boundary, which happens in the mid-Atlantic ridge, and you're going to have two crusts or two plate boundaries pushing from each other. Here's a great image because now you're also seeing the lithosphere and the asthenosphere. Okay, this is the lithosphere and the asthenosphere. The asthenosphere, if you Google that, is going to be the plastic layer of the mantle. So you have your crust, your lithosphere, and then you have your asthenosphere. And there could be some confusion between the bottom of the crust or the top of the mantle in that aspect. All right. Now, another vocabulary term that you may want to become familiar with is basically a hot spot. And there's only basically one hot spot in the world, so don't get overwhelmed. Hawaii is a hot spot. All right. Hawaii is basically a hot spot. That basically means where there is no plate boundary, rather there's just like a hole of magma that's peeking up and coming out, all right? And the Hawaiian Islands form this way. So as the crust continues to move, this hotspot is throwing up steam and forming new land as that volcano basically hardens and then moves. So magma, it's up into the ocean, it hardens. This hotspot continues to move, but the crust continues to move. So it looks like the islands get bigger and bigger. And that's basically how the Hawaiian Islands have formed. Okay, and so once again, you can have an island arc, convergent plate boundary. All of these volcanoes, once they stop being active, can form islands, and those are how islands are going to be formed. All right. Okay. We'll do a couple more slides. Now, another thing you may want to become familiar with is the Richter scale. And this is how you measure how strong an earthquake is. And something you need to take into consideration is how much damage it really causes. Okay, so you have the numbers from 1 to 10, 10 being really, really bad, okay, or really, really devastating. And it's a logarithmic scale. So that means every jump is like 10 times fold, okay? So it's a lot worse as you go up one, all right? Now, 1 through 3, you hardly feel. So that's like over here, okay? 1 through 3, you hardly feel it, okay? I think we had one. Did we have one? We had one, I think, and there was a lot of memes like earthquake in New Jersey, and there was like a lawn chair just flipped over. There wasn't anything big like that. However, you know, there has been in recent time some pretty destructive ones. And so let's go all the way to the most destructive in Chile in 1960, and that had a magnitude of almost 10. That we're talking about crazy. Krakatoa was magnitude between 8 and 9, which is a big thing as well. All right. So Hiroshima, the atomic bomb, that was in between 6 and 7. All right. In Long Island, we had one between 5 to 6. And so here is a good way to understand how much power is released. And so when those plates are pushing against each other, they're pushing against each other, push so much force that sooner or later one gives way. And that is what an earthquake is. And then if they push and they give way, that's that first earthquake. But then as they reform, they're getting at that aftershock. Okay? And think of pushing two things really close. There's going to be one shift and there might be another shift, and those are all aftershocks. What happens in between the aftershocks? Pressure continues to build on these things. Okay, so all those, the melted magma, the energy, the heat, the metals, all those stuff is pushing on each other in between those earthquakes. Okay, let's continue. Beautiful. Like I was saying before, Hawaii is an example of a hotspot. And so when we look at this, so beautiful Hawaii. Welcome back. I'm sorry, I had to take a pause there. Here, you're going to have that hotspot. There's no plate boundaries. That hotspot just brings this magma to the top. This beautiful island now forms. This hardens, it cools. And as that plate continues to shift, you see that, Hawaii is destined to make more and more islands. So if one of you get rich enough to buy your own island, I think you might have to wait for quite some time, but you could possibly invest in one of the new islands that will form from this beautiful hotspot. All right. Okay. Now, island arcs is a term used to describe basically a bunch of islands forming because of that subduction zone. Once again, a trench would form right in this area. You have that subduction zone and the land folding back on itself, and now you have a beautiful arc, a bunch of islands forming. And some examples of island arcs were going to be Japan, the Aleutian Islands, and the Galapagos Islands. All right, let's look at that. If we go over here, right, and I know that probably not the best, but we have the Galapagos, which are going to be off the coast. Over here, we have the Aleutian Islands over here, and we have Japan over here, which are a bunch of island arcs in that area. All right, all because of subduction zones. Okay, and that's going to complete our lecture on plate tectonics. I hope you learned something, and I'll talk to you tomorrow.